Okay, what's up, guys? So, let me make sure I got this working right. Yep. Yeah, that's working. All right, great. So let's get into it. If you didn't see an announcement on YO courses I posted just a little bit earlier today, I have extended the deadline on the section, or the homework due today, right? The homework due tonight until Wednesday. I got a larger than normal number of emails asking questions about it and people wanting a little extra time. So why not? No skin off my back. I'll let you do it. Actually, I mean, if you're finding the homework today difficult, I looked back through it and I went, yeah, maybe I made this one. I don't want to say I made it too hard. I feel like it's always insulting when teachers say that. They go like, oh, it made it too hard, too much for you peasants, you know. But no, I'm not. You guys can do it. I just definitely I threw more challenging problems in one assignment than I probably would have if I had been being more careful. I know you can do it, but if you feel like it's hard, you're not crazy. It's a little bit more on the challenging side compared to some of the other homeworks, or at least it's got a number more challenging problems than other ones. So everyone gets a little bit of extra time on it, and yeah, hopefully that helps out. Today we'll be starting chapter 4. Now that we've talked a little bit about series and how to deal with them in the complex world, and a little bit about how this ties in with analyticity, and we've introduced the concept of the Laurent expansion. So the Laurent expansion, if you recall, is just basically like a Taylor series, but you've got, negative exponents, right? Instead of just like first powers, second powers, third powers, so on through all of the positive integers, we also start taking in negative integers. Fair enough. The coefficient, if you recall, of the first term with a negative exponent, so that is this piece right here, if you notice, is b1 z minus c naught to like the minus 1, right? And if we can write everything out like this if we feel like it, bn z minus c naught to the minus n, so on. And we can continue this here just to be clear. I'll even write the 1 right there. There we go. So you can do something like this, and you can go through the whole thing. And well, I'm playing some beats, but these have words, which makes it kind of annoying to do things to. Here, that should just be just music. There we go. That'll be better. All right. So notice we're just basically, instead of normally with a power series, just using the positive integers and 0, of course. This is z minus c naught to the 0 at a naught. We're also using negative powers. And so this first one, b1 right here, is kind of a big deal, as it turns out. That is the so-called residue. If you remember, we say that this is the b1 is the residue of f at z naught. So this is with regard to this expansion at z naught. And remember, we don't have to like specify some sort of a domain necessarily. There is a domain associated to Laurent expansion, but this annular region is determined. It's not something that you get to choose, right? There's a maximal annular region on which the Laurent series about any given point converges. So we just have to specify the point, z naught, the function, and then we immediately get our residue from the Laurent expansion. And why this was important was because we started to look at basically the Laurent expansion version of Koshi's theorem. And this was a big deal because it starts to maybe demystify a little bit about what's been going on with certain things. For example, why is it the case that if you integrate, say, around the unit circle the function 1 over z, why do you end up getting out 2 pi I? And if you do it for z squared, why do you get out 0? Stuff like this, right? So what we got that maybe put us in this direction was proposition 3.3.3. And in this proposition, which is very important because it's basically the Laurent series version of Koshi's theorem, it says, let F be analytic on a region A and have an isolated singularity at z naught with residue B1 at z naught. If gamma is any circle around z naught in A whose interior, except for the point z naught, lies in A, then the contour integral of f about gamma is equal to the residue of f at z naught times 2 pi I. So in this sense, the residue is sort of serving a role similar to, I won't say necessarily like the index, but the residue is basically picking up something like the role of the function evaluated at the point times the index or something. And really we should be careful here because this is any circle around z naught. And so, we want to be a little careful about like indexes. Just keep it simple right now and just think of it like like a version of Koshi's theorem that is slightly more general or something to that effect. And so the calculation of residues becomes an interesting problem for a lot of reasons. Namely, and I'm going to start adopting this notation, B1, this coefficient, the residue, we'll write res f semicolon z naught to mean the residue of f at z naught. This value is obviously important because computing some of these contour integrals can be pretty annoying. In general, just doing integration can be pretty annoying. There are lots of very difficult integrals to evaluate, and even ones that are just flat out pretty much impossible, I guess, would be maybe a way to say it, though. You can do numerical approximations, but they might even be just like ridiculously expensive or very unstable, and just integrals can be kind of a beast to deal with compared to derivatives, which are surprisingly easy to deal with. So it is really nice when you get things like this, but it does involve trying to find these residues. We can calculate something that might otherwise be difficult, but we can do it in terms of residues. Okay, we have to figure out how to find the residues, though, and that's what section 4.1 is going to start to be about. We're going to start to do the calculus of residues. So we want to develop a technique for computing these guys, but we don't want to necessarily have to find the whole Laurent expansion because that just seems like, honestly, just as much of a big deal as actually computing some of this stuff. It seems like that just is a similar amount of work, or if it's not a similar amount of work, it's at least more work than we need to do, and we're mathematicians, so we're ultimately, at the end of the day, fairly lazy and want to do the minimum amount of work absolutely necessary. So if you know the Laurent expansion, you're good to go. For example, and we did this last time, e to the 1 over z, and you did this in your homework before. This is just 1 plus 1 over z plus 1 over 2z squared all the way up, the sum from n equals 0 to infinity of 1 over n factorial z to the n. So the coefficient of the 1 over z term is obviously 1, since we just have 1 over z right there. So this guy, e to the 1 over z, has residue 1 at z naught equals 0. Okay, so if you already know the entire Laurent expansion, it's very easy to see what the residue is because you're just, selecting a single coefficient in the Laurent expansion. But if you don't know it, then you need a trick to figure it out. So we're going to go through some tricks. All right, the easiest case is with removable singularities. If f is analytic on a deleted neighborhood of z naught, from section 3.3, we can recall that f has a removable singularity at z naught if and only if the limit as z goes to z naught of the quantity z minus z naught times f of z is equal to 0. So that tells us when we have a removable singularity. It means we can just get rid of it and not have to worry so much. So The following theorem will cover a lot of situations and pretty much give us most of what we need today. Proposition 4.1.1, if g of z and h of z are analytic and have zeros at z naught of the same order, then the function formed by taking g of z divided by h of z has a removable singularity at z naught. That is, having a removable singularity, the archetypal case, really the only case, is the case where you have zeros of the same order, or you have the numerator with a zero of a higher order. That is, z squared over z is just equal to z everywhere except at 0, at which point it's undefined, but you could just, you could remove that singularity and you could define a value and then you're good to go, right? So basically it's just removable singularities happen when the top function has a 0 of at least the same order as the bottom function, though it could be higher. Fair enough. So if you want to see this, proof is super simple. By proposition 3.3.4, you can write g as z minus c naught to the k times g tilde of z, where g tilde of z naught is non-zero. Okay, and you can do the same for h. Okay, obviously this is great with h tilde, and h tilde of z naught is non-zero, so g tilde and h tilde are analytic and non-zero. So if you form f of z, which is g over h, well, z minus c naught to the k, z minus c naught to the k, hey, I just have g tilde over h tilde, that's analytic at z naught. This is exactly what I'm saying about, like, for example, if you take z squared over z, you can write one, you can get rid of it, right? That's, of course, you can do the same thing. This is like the z over z example. I'm kind of getting ahead of myself. If g has a 0 at z naught of order greater than h, this is like the z squared over z case. Then g over h has a removable singularity at z naught as well, obviously, like we just talked about. So this is kind of the easiest case. Basically is when you have the top having a 0 of higher order than the bottom, or at least as high of order. Then you've got pretty much the most simple thing to deal with. When you've got the bottom with a higher order 0, it doesn't necessarily make it worse. After all, one of the easiest possible residues to calculate, considering that the residue is just this b1 term, right? One of the easiest possible residues to calculate is the residue for the function 1 over z. Oh, that's a pretty simple one, right? It's a residue. It's got a residue of 1, right? In an expansion, you can write it like that. At 0, at least, right? The residue of this function at 0 is 1, right? Okay, so anyways, couple examples just to really drive the point home. So e to the z over z minus 1. This doesn't have a singularity at 0 because the bottom isn't 0. It's a pretty easy example. So, when you're starting to do this, make sure that you're actually looking at cases where this makes sense. This does have a 0 at, the bottom has a 0 at z equals 1, right? But not at z equals 0. So, sorry, it seems like a dumb point to belabor, but I can guarantee that I will definitely see someone try to use techniques from this section to compute things that don't have singularities at a given point and therefore don't have this these theorems like right here, propositions like results like proposition 3.3.3 apply. I guarantee you that I will find people doing things without even an isolated singularity, just, with the bottom not even equal to 0. They'll just see that it could be equal to 0 somewhere else, and they'll try to apply these results to get around doing an actual computation. So be sure you're not doing that. If you want to see a non-trivial example, something like e to the z minus 1 over z, this has a removable singularity at 0 because e to the z minus 1 and z have zeros of order 1. They both go away, that are equal to 0 when you plug in 0, but their derivatives don't. That's what it means to have a 0 of order 1, right? So, in case anyone has forgotten, remember that when you write out something as a So if you write like f of z equals, we take like a power series, right? Let's write it from k equals 0 to infinity of ak z minus z naught to the k. Obviously, if the first term is equal to 0, then you have a 0 of your function at z naught, right? Okay. And now if the second term is also equal to 0, then you have a 0 at z naught for your function and for its first derivative, and so on and so on. So the first ak that is non-zero, that is the, if you remember, the order of the 0, just to be clear in case anyone has forgotten what 0 of order 1 means. So let's do another example. Z squared over sine squared z. This guy has a removable singularity at z naught. Why? Because both the numerator and denominator have zeros of order 2. You can check that pretty easily. Plug in 0, right? You'll get 0 squared over 0 squared, right? And then you repeat the process, do a derivative 2z, right? And then you can spend a while doing the bottom part, but you'll have signs in both terms, and then you plug in 0 and you'll get 0, right? And then you do one more and you just get 2 on top, and then you finally get something that doesn't have a sign in it, and then you can plug in 0 and you'll get a 1 down there. So finally you don't get a 0, so that's a 0 of order 2. Bada boom. All right, all good, pretty easy. Now, simple poles. So the easiest situation is removable singularities, but simple poles are maybe a little bit more interesting because we'll start to get to actual residues. All right. To be clear, let's do an example to drive something home actually before we do that. Here, let me just do a quick example right over here. All right, so let's do, say, z over z. How about that? That has a removable singularity at 0, right? And that's an isolated singularity, right? And z over z is analytic everywhere except at, of course, 0, right? So this should apply, right? Let's figure out what the residue is. All right. So if we integrate, say, around the unit circle, right? Let's do around the unit circle, z over z dz, right? We'll integrate from, say, like 0 to 1. I'll do e to the 2 pi I t over e to the 2 pi I t. And then that dz, remember, we have to replace it with 2 pi I e to the 2 pi I t dt, right? And hey, these guys all cancel each other out, right? So we just get 2 pi I times the integral from 0 to 1 of e to the 2 pi I t dt. Oh, well, easy enough. What do we get there? Well, what is an antiderivative of 2 pi I e to the 2 pi I t? It's 1 over 2 pi I e to the 2 pi I t, right? And then when we evaluate it at 0, we evaluate it at 1, e to the z is 2 pi periodic, right? So what do we get? Well, we'll just get wow, awesome. So easy enough. This should cue you in that unlike 1 over z, something like z over z does not have a non-zero term b1, right? Oh, okay. It's pretty obvious. So the Laurent expansion, is for f on an annular region. The annular region for z over z about 0 is the entire complex plane except for 0, right? So on the entire complex plane, it's only got one term, a naught, and it's equal to 1. So you can you can pretty easily remind yourself what's going on with removable singularities. Now, simple poles, this is like the case like 1 over z. This is where things start to get a little bit more interesting. Okay, now by proposition 3.3.4, if the limit as z goes to z naught of z minus z naught f of z exists and is non-zero, then you have a simple pole at z naught, and this limit equals the residue. So that is res, make sure I'm writing this in the same order we said we were going to do, f z naught. Yeah, okay, good. Res f semicolon z naught. This is equal to lim z goes to z naught, z minus z naught, f of z. Bada boom. As long as this exists and is non-zero, right? Okay, cool. Now, let's get this useful method. Here's a useful method for computing residues. Blah. So proposition, let me get my highlighter out and get a better color. 4.1.2, if g and h are analytic at z naught and g of z naught's not equal to 0, h of z naught is equal to 0, and h prime of z naught is not equal to 0, then the function f of z equals g of z over h of z has a simple pole at z naught, and the residue of f at z naught is g of z naught over h prime of z naught. Oh, okay, let's try this out. So since h of z naught is non-zero, by the definition of the derivative, well, the limit as z goes to z naught of h of z minus h of z naught over z minus z naught, this is h prime of z naught, right? Well, h of z naught is 0, so that just goes away, right? And so we have the limit as z goes to z naught of h of z over z minus z naught. This is h prime of z naught, and that's not equal to 0. Okay, so just flip everything over. The limit as z goes to z naught of z minus z naught, that quantity divided by h of z is 1 over h prime of z naught. How about it? You can also do other things if you want to get there a different way. For example, like a logarithmic. Never mind. You know, easy enough. Okay. Therefore, the limit as z goes to z naught of z minus z naught, g of z over h of z. Well, you have a convergent piece right there, and g of z. All right, all good. So it's g of z naught over h prime of z naught. We're all good to go. Bada boom. That's what we wanted. Oh, okay. But wait a second. This exists and is non-zero, and the limit equals the residue. So that is the residue. How about that? Kind of nice. This is pretty convenient. So one thing that I asked you to prove on the homework that was due tonight but is no longer due tonight is L'Hopital's rule. L'Hopital's rule. Proposition 4.1.3 basically is an application of L'Hopital's rule to the previous result. It's got the shortest little proof. So here we're going to suppose that g of z has a 0 of order k at z naught, and that h of z has a 0 of order k plus 1. Then g of z divided by h of z has a simple pole with residue given by the residue of g over h is equal to k plus 1 times the kth derivative of g at z naught divided by the k plus 1th derivative of h at z naught. Comparing, notice g z naught, h a derivative of 1 order higher at z naught. Exactly the same thing going on here. We've just got a k plus 1 over there, right? Nothing too fancy, yeah? Okay, cool. So how do we get there? It's just an application of L'Hopital's rule. So the limit as z goes to z naught of z minus z naught of g of z over h of z, we just keep applying L'Hopital's rule until we get down to a situation that looks like this, right? Oh, okay. So all we have to do is observe that both z minus z naught times g of z and h of z are analytic at z naught, with z naught a pole of or 0 of order k plus 1. Hence, after we take k plus 1 derivatives, right? After all, that's the the definition, this first non-zero term, we get something that's non-zero, and then we're good to go, and we can stop using L'Hopital's rule, right? We don't get an indeterminate form anymore. So let's do some examples, because all of this feels, I think, kind of abstract, and so you start actually using it, and you go like, oh man, this is super easy. This is so simple to use. This is fantastic. So let's do a little bit of it. First one, let's try it out. E to the z divided by z at z equals 0. Okay. So 0 is not a 0 of e to the z, but it's a first order 0 of z. All right. So the residue at 0 is 1 times e to the 0 over 1 equals 1. Wait a second. How are we getting there? Well, e to the z over z. So here, top function, non-zero. Bottom function is 0. Derivative of bottom function evaluated at point is not equal to 0. Right? So the residue is top function at z naught divided by bottom function's derivative at z naught. Okay, so at 0, top function, so top function's at 0, that's 1, right? Bottom function's derivative at 0, well, it's just 1, so we get 1. Easy, right? Super simple. Okay, what about e to the z over sine z at 0? Here, remember, e to z is not 0 at the point z equals 0, obviously, just like before. And since sine of 0, or sine prime of 0, I hate that they write it like that. The derivative of sine z evaluated at 0, that is cosine of 0, is 1. 0 is a first order 0 of sine z. Easy. Okay, so the residue is top function evaluated at 0 divided by derivative of bottom function evaluated at 0. That's 1, once again. Oh, okay. So any integral, or any circle, if we want to just, let's be very careful and state things exactly like in proposition 3.3.3. So if we take any circle around 0 in the domain of analyticity of e to the z divided by sine z, which is the entire complex plane minus 0, or really I should actually be careful, minus the zeros of sine z. So any circle in that region surrounding 0, then what do we get out of an integral? We get out 2 pi I, because the residue is 1. Easy. So what about, say, z over z squared plus 1? Oh no, bottom has a higher order 0 at z equals I than the top, because the top is non-zero. Easy. Okay, so g of z is z, h of z is z squared plus 1, g of I is I. That's not equal to 0. This is a great idea, or this is a great indication that we should use proposition 4.1.2 every time you see the top function not equal to 0. It should give you some idea that maybe you're going to do something like this. Okay, so top function, non-zero. Bottom function, plug in I, well, we're going to get 0. H prime of I, well, it's 2z. Plug in I, 2i. That's non-zero. So the residue is top function evaluated at I divided by bottom function's derivative evaluated at I. That is 1 over 2, and they have missed something. Ooh, have they missed something pretty bad? Yeah, they missed that. Ooh, h prime of I is 2i. They didn't put that there. 1 over 2i. So if you evaluated, say, this guy around a circle centered at I in its domain of analyticity, what would you get out? 2 pi I times 1 over 2i, so you get out pi. Easy. All right, what about, say, z divided by z to the 4th minus 1 at z equals 1? Obviously, you plug z equals 1 on the bottom, you're going to get out 0. On top, you're going to have something that's not 0, so it's a great situation to use that. All right, but wait a second. Okay, let's see. G of z is z, h of z is z to the 4th minus 1, g of 1 is 1, that's not equal to 0, h of 1 is 0, obviously, So we're pretty much in the situation we're going to be. Take a derivative just to make sure we don't have to do anything fancy, like start to use proposition 4.1.3 instead. We're still good because take a derivative, you get 4z to the third, and you plug in 1 and you get 4, right? H prime of 1 is 4. That's not 0, so the residue is 1/4. Easy. Okay. Z over 1 minus cosine of z at z equals 0. Obviously, the bottom is equal to 0. Top is also equal to 0. Ooh, okay. G of 0 equals 0. And G prime of z equals 1. That's non-zero. So 0 is a simple 0 of g, right? All right. Fair enough. It just is 0 of the function and not its derivative. H of 0 is 0. H prime of 0 is 0. Fair. H double prime, though, is 1. That's non-zero. So 0 is a double 0, or a 0 of order 2 of H. Okay. So now we're going to use proposition 4.1.3. In this case, we'll take k plus 1 times the kth derivative of z naught, of g at z naught, divided by the k plus 1th derivative of h at z naught. So in this case, remember, g has a 0 of order k, h has a 0 of order k plus 1. Here we have a 0 of order 1 and a 0 of order 2, right? So we'll take 2, that's 1 plus 1, k plus 1, g to the kth derivative of g, that's the first derivative of g, evaluated at 0, divided by the second derivative of h, evaluated at 0. So that's 2 times 1 over 1, it's 2. All right, and wouldn't you know it, that's the residue. Yeah, the residue at 0 is 2. All right, so as you can see, this is not really that bad to use. And via proposition 3.3.3, which is kind of this new version of Koshi's theorem for us, a useful trick, this will let us get at a lot of contour integrals. It will do a lot of nice things for us. So we will, in fact, this turns out to be useful in, well, we'll talk more about how this is useful. Right now, we'll just focus on calculating things. Really, it just comes down to simple things like this, where you just basically are doing one more derivative on the bottom than the top, and occasionally you need a correcting factor of how many derivatives you did on the bottom. And then you get at the residue. Easy. All right, so I think that's a good place to end it right now. We'll deal with some slightly more complicated cases that really aren't that bad. They're just mild extensions of this next time. And I'll, since people wanted to work on the homework a little more, I'll give everyone back a few extra, about 10 extra minutes, 15 extra minutes of your night today, and start the week off good on a Monday. So I think that wraps it up. Hope you have a great night. Email me with any questions you have on the homework. See ya.